let us discuss about the electrophilic substitution in phenol. That is how the phenol is undergoing electrophilic substitution reactions that can be understood by taking the resonance structures of phenol. Yes, take the phenol. Okay, here the oxygen is having lone pair of electrons. This OH is the hydroxyl group is electron donating group. The hydroxyl OH group is electron donating group. It activates the benzene ring, benzene ring at ortho and para positions. Okay, that is why the incoming electrophile attacks at ortho and para positions. Okay, yes, here the hydroxyl group is electron donating group. It donates electrons to the benzene ring like this. Okay, so you know that the carbon must have only the 4 bonds. Here this carbon is already having this side 1 bond, 2 bonds, this 1 bond, 4 bonds totally, and when it makes a double bond here, this bond has to shift. Okay, now the conjugation or resonance starts. Okay, yes, here we have one OH with one lone pair of electron, and it has another lone pair, and it has become a pi bond here. Okay, and it is becoming a negative charge here at this carbon, and these pi bonds are not disturbed. Okay, and it is unstable. That is why what happens, it jumps to this. So here this jumps to this position, that is OH double bond OH, here lone pair of electrons on the oxygen. Okay, the positive charge here, and here it is making a double bond. Okay, and here there is a negative charge, and it is undisturbed, and this molecule is also unstable, so it jumps here, so that the pi electrons jumps here. See here, this double-headed arrow is representing the resonance structures. Okay, yes, here we get the structure as OH. The oxygen is having lone pair of electrons on the positive charge and the negative charge, and double bond here, double bond here. Okay, this is also unstable. It jumps the electrons here, and it takes back its electron. The oxygen takes back its electron and becomes the double bond here, here also. Okay, and here we can see the OH again with the 2 lone pair of electrons. Okay, these are the resonance structures of phenols. Okay, these are the resonance structures of phenols. Okay, when you consider the first compound and the fifth compound, first and fifth compound, here you can see the changes in position of the pi bond. Okay, here there is a pi bond, and here there is no pi bond. See, here the pi bonds are not fixed at the positions, or pi electrons are not fixed at the positions. You know that these are continuously delocalizing on these 6 carbon atoms of a benzene ring. Okay, and when you look at the structures too, where there is a rich in electron density, at this ortho position, you can see the rich in electron density. Okay, when an electrophile enters, that attacks at this ortho position. Okay, and when you look at the structure 3, where there is a electron rich density, here. Okay, that is at a para positions. Okay, when an electrophile enters, that attacks at the para positions. Okay, yes, when you look at this fourth compound, where there is rich in electron density, at this ortho position. Okay, so that is why in the phenol, the electrophilic substitution takes place at ortho or para positions. Okay, because of rich in electron densities at these positions. Okay, yes, this is about how the electrophilic substitution takes place at ortho and para positions. Okay, and here out of the ortho and para products, para products will be more stable because of less steric hindrance or steric repulsions. Okay, and when you consider the ortho positions, these when the groups are present at the ortho positions, these may have the repulsive forces. That is why it is somewhat less stable. The ortho products are less stable compared to the para products. Okay, and here the phenol may undergo the electrophilic substitutions like halogenation, nitration, Friedel-Crafts alkylation, acylation, the sulphonation reactions, even Kolbe's reactions, and Reimer Tiemann reactions, etc. Dear students, now we shall consider about the electrophilic substitution reactions in phenols. Okay. Yes, here we have to discuss about the nitration of phenol. Okay. And secondly, the halogenation of phenol. Halogenation of phenol. And third one is Kolbe-Schmidt reaction. Kolbe-Schmidt reaction. And the fourth one is Reimer Tiemann reaction. And the fourth one is Reimer Tiemann reaction. Yes, these are all considered as electrophilic substitution reactions. Means one of the hydrogen atom of the benzene is replaced with the other electrophiles. And that leads to the electrophilic substitution reactions. Okay. Firstly, we shall consider about the nitration. Okay. Firstly, we shall consider about the nitration of phenol. Okay. Nitration of phenol. Dear students, now we shall consider about the nitration of phenol. Here, two cases arises. One is nitration of phenol with dilute nitric acid gives some products. Okay, and the nitration of phenol with concentrated nitric acids give other kind of product. Let us observe the differences between the nitration of phenol with dilute and concentrated nitric acids. Firstly, we shall consider the nitration of phenol using dilute nitric acid. Okay. Yes. Here, when the phenol is nitrated, okay, using dilute nitric acid, at low temperatures, okay, gives the ortho or para nitrophenols, gives ortho. What is this? This is ortho because 1, 2 positions are called as ortho nitrophenol. It is ortho nitrophenol. Okay. See here, we have oxygen atom here and hydrogen. Here, there may be chances of intramolecular hydrogen bonding. Here, orthonitrophenol executes, okay, intramolecular hydrogen bonding. Okay. Yes. And come to the next product, that is para-nitrophenol. Here the para-nitrophenol makes intermolecular hydrogen bonding. Makes intermolecular hydrogen bonding with other molecules. Okay. See, when phenol is treated with a dilute nitric acid at low temperatures gives orthonitrophenol, and the orthonitrophenol is making intramolecular hydrogen bonding, and the another product here is para-nitrophenol. One para-nitrophenol makes between intermolecular hydrogen bonding with other para-nitrophenols. Okay. Yes, intra means within the molecule, inter means between the molecules. Okay. Due to these differences, the orthonitrophenol is steam volatile. It is steam volatile. Okay. Means when a water vapor at high temperature, that is steam, is passed through the orthonitrophenol, it evaporates because of its steam volatility. Okay, and it is non-steam volatile. The paranitrophenol is non-steam volatile. Non-steam volatile. Okay, here when you treat the phenol with the dilute nitric acid, you are getting two products. And how to separate these two products? By steam distillation technique. Okay, separation of these products can be done by steam distillation. Okay, separation of ortho and para nitrophenols. Ortho and para nitrophenols can be done by steam distillation technique. Can be done by steam distillation technique. Now let us discuss about the nitration of phenol using concentrated nitric acid. Okay, take the phenol, okay, and treat this with concentrated nitric acid. See here, the hydroxyl group is electron donating group. It activates the benzene ring at ortho and para positions. Okay. Yes. Let us consider this. You can see the replacement of hydrogens present at ortho and para positions by the NO2 groups. Okay. Now this is called as picric acid. Okay. And it is a yellow crystalline solid. Yellow crystalline solid. It is used in explosives. Because of its high acidic nature. See here, this is the phenol. Okay, here the H plus ion is ready to come out because of presence of 3 electron withdrawing groups. This will pull the electrons towards itself, then it readily ejects this H plus ion. Means it is the strong acid. Okay, out of all the phenols, okay, and even in comparison with the carboxylic acid, it is a strong acid, but not as strong as HCl, H2S4, HNO3, because those are mineral acids. Okay, yes, among the carboxylic acids and phenols, this is the a strong acid. Okay, yes, and what is the IUPAC name of this compound? See, this is the major functional group. These nitro groups are substituents, and what are the positions? This is 1, 2, 3, 4, 5, 6. So where you can see the nitro groups at second, 4, 6. Okay, I can write the IUPAC name as 2, 4, 6 trinitrophenol. So how you can get this trinitrophenol? By treating the phenol with a concentrated nitric acid. Okay, and you know here the OH group is ortho para directing group because it is an electron donating group. Okay, and here the 3 nitro groups are present at 2, 4, 6 positions. Therefore the IUPAC name is 2, 4, 6 trinitrophenol. Its common name is picric acid, and it is a yellow crystalline solid, and it is used in making of explosives. Okay, because of its highly acidic nature. Okay. Now we shall consider the second reaction, that is halogenation of phenol. Here also there are 2 types of reactions. One is using the halogen. Here we shall use the bromine. Bromine in presence of the low polar solvents like carbon disulfides and chloroform. That gives one type of product. Okay, and another one is using bromine water. Okay, let us consider the first case. Okay, the bromination of phenol, bromination of phenol in less polar solvents, like CS2, carbon disulfide, or chloroform, that is CHCl3. Okay, let us consider this reaction. Take the phenol and treat this with bromine in the presence of carbon disulfide. Okay, that is bromine in carbon disulfide. It is a less polar solvent. Okay, so what happens, this OH group is ortho-para directing group. Okay, ortho-para directing group. Therefore you will get the orthobromophenol as one product. What is this? O, that is one for 1, 2 positions we call orthobromophenol, and there is another product, that is parabromophenol. Okay, parabromophenol. Say, out of these two, which one is the major product? The one with the least steric repulsions is more stable. Okay, and that will be the major product. Here OH group and para group are opposite in directions and there are less repulsions, therefore it is stable and it is considered as a major product. And here this one will be considered as a minor product. Ortho products are minor because of steric repulsions between these two groups causes repulsions and it is less stable. Okay, so amount for formation of this compound will be less in quantity, and here there is less steric repulsions and this type of product will be formed with a good yield, therefore it is considered as a major product. And comes to the IUPAC name. See, this is position 1 because a carbon containing functional group gets the least number. This is position 2, so it is a 2-bromophenol. Its IUPAC name is 2-bromophenol. And come to this is a 1, 2, 3, 4. So this is a 4-bromophenol. Okay. Yes. So this is all about the bromination of phenol in less polar solvents like carbon disulfide or chloroform. Okay. Let's consider the bromination of phenol in polar solvents like water. Okay. Yes. The second one is bromination of phenol. Bromination of phenol in polar solvents. Like water. Water is a good polar solvent. Okay, let's consider that is using bromine water. What is bromine water? The bromine is taken in water. Okay, using bromine water. Yes, take the phenol and treat this with bromine water, that is bromine in the presence of H2O. So what happens, as you know that the OH group is ortho-para directing group. Okay, here the phenol where OH group is ortho-para directing group, it activates those positions. The hydrogens present initially at ortho and para positions are replaced with the bromine. Okay, so now you are getting the positions 1 to this carbon because it is containing a major functional groups, 2, 3, 4, 5, 6. Therefore, it is 2, 4, 6, tribromo tribromo phenol, and it is a white colored solid. It is a white solid. Okay, yes, this is all about the bromination of phenol in less polar solvents and bromination of phenol in polar solvents like water. Okay, so when you conduct the bromination of phenol in less polar solvent like carbon disulfide, you will get ortho and para bromophenols. Okay, when you do that bromination in highly polar solvents like bromine in water, you will get a 2,4,6 tribromophenol, and it is white in color. Okay, now we shall discuss about Kolbe-Schmidt reaction. Okay, here in this reaction, the phenol is initially treated with sodium hydroxide, and gives the sodium phenoxide, like this. Okay, gives the sodium phenoxide. Okay, it is sodium phenoxide. When this sodium phenoxide is treated with carbon dioxide, here carbon dioxide is a weak electrophile. It is going to replace the hydrogen of the benzene ring. Therefore, it is undergoing electrophilic substitution reaction. Therefore, I already mentioned that it is a electrophilic substitution reaction. Okay, and after acidification, okay, it will give a salicylic acid as the product. Okay, salicylic acid as the product. Okay, so what is its name? Salicylic acid. Salicylic acid, it is a common name for this compound. Okay, let us recall this. Here phenol is treated with the sodium hydroxide and it is becoming a sodium phenoxide ion. Say this sodium phenoxide ion is a stable compound. It readily undergo electrophilic substitution reactions even with a weak electrophile. So carbon dioxide is a weak electrophile. Okay, yes. Firstly, we have to treat the sodium phenoxide with carbon dioxide in one step. Okay, here I have written one. Okay, and later we have to acidify that compound. Okay, then you will get the salicylic acid. And what is its IUPAC name? Here we have to identify the major functional group. The major functional group is COOH and its position is 1. Okay, and here we should not go in this order because it gives the highest number, so we have to go in this way. So it is a position 2. So minor functional group is hydroxy, so therefore we have to write 2-hydroxy benzoic acid. Yes, what is the IUPAC name of salicylic acid? 2-hydroxy benzoic acid. Okay, yes, it is a type of electrophilic substitution reaction. Okay, so this is all about the Kolbe-Schmidt reaction. Okay, yes, here you can get only the ortho product. There is no para product here because of the reaction. Here you may also see the insertion of the carbon dioxide into this at this ortho position, but not with the para positions. That is why you can get one product that as a major, that is a salicylic acid. Okay, yes, here let's go for the fourth one, Reimer-Tiemann reaction. Let's discuss about the Reimer-Tiemann reaction. It is also one of the electrophilic substitution reaction. It is also considered as electrophilic substitution reaction. It is also considered as electrophilic substitution reaction, and here the electrophile is dichlorocarbon. Here the electrophile is dichlorocarbon. Here the electrophile is methylene carbon. Okay. So what is carbon? You have heard of free radicals, carbocations, carbanions, and the fourth electrophile or intermediate is carbon. Okay, it is like this: CCl2. Here the carbon is having two electrons. Okay, here the carbon is having two electrons. These are non-bonding electrons. Okay, yes. Now let us consider the reaction equation for this. Now let us write the reaction equation for this. Here phenol is treated with the alkaline chloroform. Phenol is treated with the alkaline chloroform. What is alkaline chloroform? Here chloroform is mixed with the aqueous NaOH. Is mixed with the aqueous NaOH, and this makes the basic chloroform or alkaline chloroform. It acts on the phenol and gives this compound. Here the OH is became ONA, and here there is a CHCl2, and when this compound is further heated with the NaOH, you can see this compound as ONA. Here CHO. You can see the aldehyde group is present already. Now this CHCl2 has come from this CCl2. Okay, that is a dichlorocarbon. Okay. Now where the chlorines are replaced with the oxygen, so you will get a CHO, and when this is acidified, you will get the salicylaldehyde. You will get the salicylaldehyde like this. Okay. See here, the major functional group is CHO and its position is 1, and minor functional group is OH, its position is 2. So what is the common name of this compound? Salicylaldehyde. Salicylaldehyde is the common name of this compound. And what is the IUPAC name? 2-hydroxybenzoaldehyde. 2-hydroxybenzoaldehyde. 2-hydroxybenzoaldehyde is the IUPAC name. And this is about the Reimer-Tiemann reaction. Say in the Kolbe's reaction you will get the ortho product. In the Reimer-Tiemann reaction also you will get the ortho product. And Kolbe's and Reimer-Tiemann reactions are examples for electrophilic substitution reactions. In the Kolbe's reaction, the electrophile is carbon dioxide. It is a weak electrophile. And in the Reimer-Tiemann reaction, the electrophile is dichloromethylene carbene. This is okay. Yes. Now let us discuss about the oxidation of phenol. Here there is a natural oxidation of phenol process, and you can also do the oxidation with some chemical reagents. Let's see the two methods also. One is the normal or natural oxidation of phenol. Okay, that is atmospheric oxidation. We can call it as a atmospheric oxidation. Atmospheric oxidation of phenol. Atmospheric oxidation of phenol gives the parabenzoquinone. Parabenzoquinone. It may be pink in color. Dark or brown, any color. Okay. Yes. Let us consider the reaction equation for that. Take the phenol and make it to exposure to air or oxygen, okay, and it becomes oxidized to, okay, para-benzoquinone, okay, like this, okay, and it may be pink in color, sometimes dark or brown in color, okay. Say, take the bottle of phenol. It is a volatile solid, as we have discussed in the properties, physical properties of the phenol. It is a volatile solid. Take the bottle containing phenol and keep it open. After some time, you can see the pink color or brown coloration upon the surface of the bottle, okay. Yes, that is due to the oxidation of phenol to benzoquinone, okay. Yes, and you can also perform some chemical methods to oxidize the phenol, that is using chromic acid. Using chromic acid. What is this chromic acid? Sodium dichromate, that is Na2Cr2O7, in presence of H2SO4. Let's take that. When phenol is treated with sodium dichromate in presence of H2SO4, gives the benzoquinone, with the release of water. What is this compound? Para-benzoquinone. Okay.